Okay, so now that we know about the valence shells and the ability to fiddle with the electrons in it, we have to talk about bonds. These are different types of bonds, covalent, ionic, and hydrogen, but they all involve interactions with electrons. Atoms and molecules can share electrons, or you could just outright donate an electron to another atom or molecule. Conversely, you can outright just get as a gift an electron from another atom and molecule. So when bonds are formed, they trap energy in them. When bonds are broken, that energy then becomes available for use. Think of the picture of this water molecule here, right? It's kind of like a head of a Mickey Mouse. So you have the face, which is oxygen, and then you have the ears, which are hydrogens. One molecule of water has two covalent bonds that join each hydrogen atom to the oxygen atom. Listen to that again. One molecule of water, which is the entire Mickey Mouse head, one molecule of water has two hydrogen atoms covalently bonded to an oxygen atom. This is usually where students are like, whoa, I didn't have a good definition of atom and molecule. Right, so a covalent bond or an ionic bond or hydrogen bond can bond together atoms and create a molecule. The problem here with Mickey Mouse is that the oxygen atom has a greater affinity or attraction for the electrons than a hydrogen atom does. Right? And this does make sense. It totally makes sense because the oxygen has 8 protons in its nucleus, and either one of the hydrogens, even combined, the hydrogens only have 1/4 of the attractive power of the oxygen with its 8 protons. And so what ends up happening is that all of the electrons, they kind of like have this little party down here by the chin of the Mickey Mouse heads. And so most of these electrons, even these two, they all spend time down here. And nobody likes to spend time out here in the Mickey Mouse ears because there's nothing to be attracted to out there. Right? So thinking about this, that even in a molecule, the nucleus of an atom can draw the electrons to it and create an electron party at one place on an enormous molecule. An ion is an atom that has just lost or gained electrons from its valence shell. And by doing this, we get either a positively charged or a negatively charged structure. Don't be fooled that you can make an ion by gaining or losing a proton. You cannot. If you want to try, you get a big explosion, radiation sickness, and B horror movies. I am using lithium as an example here, not because we see it often in this class, but because it has an atomic number of 3, making it really easy to count those subatomic particles. In the middle of the lithium atom, and in its juicy filled nucleus, are the protons and neutrons, of which 3 you can see each of which has 3. I know it has 3 protons in the nucleus and 3 electrons flying around in the shells because I know that the atomic number of lithium is 3. If I obtain the atomic mass of lithium from the periodic table, I find it to be 6. And if we employ our little equation about how to calculate the number of neutrons, I would have the atomic mass equals the number of protons plus the number of neutrons. Or I would have 6 equals 3 plus I don't know. And so there's 3 neutrons in the nucleus of a lithium atom. If I remove an electron, it leaves this atom with 3 protons and 2 electrons, and it gives it a net positive charge with that proton that's no longer matched with the electron. And this is what's called a cation. Cations have more protons than electrons. There can be one more proton or two or three. If this atom gains an electron from someone else, then it will have a net negative charge with one more electron than proton that you can see here on the right. And this would be an anion where there are more electrons than protons. Remember, I cannot trade protons to make ions. I can only trade electrons. And for the purposes of our class, it's always electrons in the valence shell. Ionic bonds they're exactly what they sound like, attraction between a cation and an anion. But first you got to make the cation and anion. In this picture here, I have ionic reactions that make two salts, sodium chloride and magnesium oxide. Notice how there are cations that give an electron, or plural, to an anion that accepts the electron. It's as simple as that to make ions. And then they attract to each other in an ionic bond. There's no touching, there's no hand holding, there's just ions kind of standing next to each other and saying, I'm attracted to you. And that seems to be enough for ions. These diagrams, these atoms down here, they don't use the planar model. These are kind of like abbreviated planar model diagrams, and what they're only showing you is just the valence shell. Each red dot is an electron in the valence shell. So I have a sodium atom here. Its atomic number is 11, so it has 11 electrons. 2 go in the first shell, 8 go in the second shell, and then I have this one lonely electron all by itself in this third shell, which is the valence shell. Again, this is kind of bad, right? Sodium would love to give this away because if it gives away this electron, then its second shell will be full and every electron will have a partner. This here is a diagram of chlorine. Its atomic number is 17. And to make a long story short, it has 7 electrons in its valence shell, which wants to hold 8. And it's almost like a match made in heaven, right? The sodium has 1 extra electron that it does not want. And the chlorine, it needs 1 electron, right? Like it just needs 1 more to fill that valence shell that it has there. This is how a salt is formed. The sodium atom gives an electron to the chloride atom. And then the sodium becomes positively charged. It's a cation, right? Because now it has 11 protons, but it gave away an electron, so it only has 10 electrons. The chloride atom, it becomes a negatively charged ion called an anion, right? Because now it has 1 extra electron compared to the number of protons it has. Magnesium and oxygen, they do pretty much the same thing to form an ionic bond. We get a magnesium cation, an oxygen anion, and then they become attracted to each other. In this instance, though, the cation has donated 2 electrons to the oxygen instead of just 1. All of this means it really is about that outer shell, right? That valence shell determines the ability of an atom to make bonds with other atoms, molecules, compounds, and other chemistry type nouns. Sorry. By trying to fulfill these 2 rules, right? That I want my valence shell to be full and I want all my electrons to have a buddy. By trying to fulfill those 2 rules, bonds are made, bonds are broken, ions are formed, and this is what is happening inside of you right now. And now. One more. Now. It's important to realize that you have electricity running through your body. A thought is really just the movement of electricity. So move your big toe. And electricity just zapped through your spine, down your sciatic nerve, and it brought a message to your toe muscles that they should contract. The electricity that your body uses to move around information, it depends on ions that are present in your blood. It depends on your interstitial fluids between cells. It depends on your cells themselves. Therefore, we call salts or ions, we call them electrolytes when we consider them in blood. And it's a word that denotes the ability to conduct an electrical current. When a salt is absorbed into your blood from your small intestine, it immediately breaks apart into its anion and its cation. So the salt you ingested at lunch immediately split into a sodium cation and a chloride anion right away when it hit your blood. And this splitting is called dissociation. This is what you see in a flask on the right in this picture. The cations and anions are fully separated because sodium chloride is a very strong electrolyte. There's also weak electrolytes, and I'll let you figure out the beaker in the middle. But with weak electrolytes, as you can see in the picture of a weak electrolyte, it doesn't dissociate completely in your blood. In fact, it really doesn't dissociate at all, right? So anything that isn't an electrolyte does not dissociate and usually doesn't help us with transmitting electricity. The molecule in the flask on the left, it could be an alcohol, which stays intact when you put into water. Could be a bunch of substances that stay intact.